Thank you very much for the invitation, for organizing the seminar. And thank you to everyone for coming after such a long day, for most of you. Even though I think in St. Petersburg the day never really stops, as I saw.
A little too loud.
Okay. Sorry. So, yes, I'm in Moscow until only for 1 more month, and then I'll be back in Marseille. But it's not so important because I will present mainly results which are not mine. I will kind of survey the area of computability theory and links with multidimensional symbolic dynamics. And I will not really get into the proof, so I will, and sometimes even definitions I will not be very formal. But if you need, I mean, I can answer all questions, and please ask questions if it's not formal enough, or if it's not, even the vague idea is not clear enough. So I can do this, yes. So basically, my talk is about two-dimensional SFT, which are two-dimensional subshift of finite type. And I have 1 slide before and 1 slide afterwards. So the slide before is about one-dimensional subshift of finite type. What is the setting? We're given a finite alphabet, which I represent as colored squares. And I'm interested in the set of bi-infinite words over this alphabet, like this, if you consider that this is bi-infinite. And so you can put the product topology of the discrete topology on this set and look at, and also since it's indexed by z, you can have a natural action by the shift of z. And you could look at closed, topologically closed shift invariant sets of a to the z. And another definition for this is a so I don't have the pointer. Another definition is the set of such bi-infinite words that I sometimes called configurations, which avoid a finite set, which avoid a set of finite patterns. And patterns are basically finite words. So, for example, if I want to avoid pattern white-white, I look in every window. Well, size 2 is enough, but and I look everywhere if I see pattern white-white, and if I don't, then my configuration is in the subshift defined by this set. Here the set is finite. When the set of patterns is finite, we call such a set of configuration the subshift of finite type, SFT. Okay, so as I said, it can be both defined by avoiding finite patterns like this, or like by shift invariant closed subsets. So there is a natural dynamical system by the shift map. And the one-dimensional symbolic dynamics is born from the theory of dynamical systems because it's a way of encoding naturally in a finite way some orbits, and so I don't know if I need to go further in this. Sorry?
It's okay.
It's okay, yes. It's just a motivation. There was also a motivation from computer science. For example, such sets as subshift of finite type are used in coding theory. So, as a dynamical system, we can ask very topological dynamical systems. You can ask very natural questions like: is there a periodic orbit? Is there a dense orbit? What is the entropy? The entropy is more or less represents how the number of patterns will grow. And but even before this, a quite trivial question is whether the system is empty, because if I'm given just a set of finite patterns, I mean, is there at least one configuration which avoids all of these patterns? It's not a priori obvious. But here in one-dimensional subshift of finite type, you can always recode your subshift of finite type by some kind of finite graph. For example, here I memorize whether the last letter I saw is a yellow or a white, and if it's a yellow, I can see everything is authorized, but if it's a white, I have to go back to the yellow after this. This is also represented by this matrix. So this kind of representation helps a lot for algorithmic questions. And so another way of seeing this is a kind of finite automaton, for those who prefer the terminology. And so it's easy once you have computed this to see whether there is an infinite path on this graph. Then this infinite path corresponds to an orbit, so the system is non-empty. In that case, there is always a periodic one, so the two first questions in that setting are equivalent, because you are in a finite graph, so if you have an infinite path, there must be one which goes twice to the same vertex. Dense orbits the existence of dense orbit corresponds to the strong connectedness of the graph, and the entropy can be computed as the logarithm of the by the logarithm of the spectral radius of the matrix. Okay, so you have basically algorithmic answers to most dynamical questions.
Are there some connection with eyes problem, you know, about the two nilpotents? Okay.
I don't know, sorry.
Maybe. Looking at your picture and matrices, I remember well-known problem about free group, which appeared when this is one matrix and second matrix is upper.
Okay. So when you have a set of matrices, then it corresponds to it will correspond to a labeled graph, yeah, or an automaton with several letters, and then this will correspond to the class of subshifts which are suffix subshifts, where you take the graph and you can label the. And for example, you may label two arrows by distinct letters, and then you may have more sets. And so it's a strict subclass, but everything is decidable also. And this is equivalent to having the set of finite patterns appearing in these configurations in the subshift to be a regular language. But I don't know if it has a link with, maybe we can discuss later. Okay, what happens in dimension 2? So I put the same definitions, I just put an exponent 2 over the z. So here is a configuration. And for example, I didn't write a set of finite patterns, but you see that this configuration avoids pattern blue horizontally, among others. And yes, maybe all definitions work quite fine. Maybe the only one where you have to be careful is the periodic. But in the context of two-dimensional subshift of finite type, you may take any natural definition and they will more or less coincide. So here, for example, yes, if there are two non-collinear periods, then you will say that the configuration is periodic. Okay. So in my subshift of finite type, it's the same. I just may have two-dimensional patterns. So here, you see that if you allow only the 3x3 patterns that you see in this picture, can you be convinced that you define a subshift of finite type where all configurations look more or less like this one, or like something with only yellow, or like something with only white. But if you have a blue, then you must have yellow on the left and white on the right. So yes, so basically the closure of the orbit of this depicted configuration is the subshift of finite type. Here is another example of, I want to say a subshift of finite type, but again I didn't define the whole family of patterns which defines it, because there are 5 letters, it's very long to write. Imagine 5 letters and you allow only patterns, 3 by 3 patterns that you see on this picture, and then it forces the red thing to behave like a kind of signal, and the green also, and it forces them to synchronize when they see a blue. What does it mean? It means that if I define the subshift of finite type, which is obviously depicted by this picture, already you see some not completely trivial things occurring. For example, if I take the set of lines here, it's no more a regular language, because if you see a red, a blue, and a white, then you know that the distance between the two should be equal. So it's a context-free language for those who know about language theory. And you can do much worse than this. Actually, the subshift of finite type corresponds to the formalism of Wang-Tile sets, which has been used in logics and which involves very complex computation. So one way of seeing this also is by relating them to cellular automata. So a cellular automaton is a map. Here, a one-dimensional cellular automaton is just you're given a local map which tells you, given a finite pattern, a new letter. And if you draw it like this with the new letter just above, you can obtain a global map when you have a one-dimensional configuration, and you apply the local rule in parallel everywhere. And if you iterate, you have a two-dimensional picture. And actually, so this is called the space-time diagram of the cellular automaton, bidirectionally. Maybe sometimes we want to require that the cellular automaton is bijective, so that we really can extend it to the bottom. But when you have this property, you see that if you take this shape for pattern and you only allow patterns with this shape that correspond to the application of the local rule, then the set of two-dimensional pictures that you obtain like this is exactly a subshift of finite type. So space-time diagram, sets of space-time diagrams of cellular automata is a particular case of subshift of finite type. But cellular automata are known to be a computational model. So you can easily embed Turing machine computation in a cellular automaton. And the halting problem can be reduced to the reachability of a particular configuration in cellular automata. So in particular, you get modulo some details that I would be happy to tell you if you have questions after the talk. But of course, I said that I cannot get into all the proofs very deeply. But you get the undecidability of the tiling problem with seed. What is it? Basically, you are given a set of constraints of local patterns that you want to avoid, and one particular cell, and you're asking, can I extend this color into a bi-infinite configuration, a bi-dimensional configuration, which avoids all the finite patterns. This is undecidable because basically you can encode the Turing machine problem in this problem. So remember that this is the set of extendable patterns. It's the set of things that you can tile without involving any forbidden pattern, but also that you will be able to extend to Z2 without involving forbidden patterns. And this is when you take as an input the set of tiles, but there also exists one universal Turing machine, and when you reduce the problem of accepting a word by the universal Turing machine, you get that there exists a specific SFT, a fixed SFT, which has an undecidable language, which means if I am given a finite pattern, can I extend it in a valid way to Z2? This is undecidable for a fixed subshift of finite type. So you already have very complex, very strong computational power. So what can we do? It's already a bit undecidable, but what can we do when we are given a family of finite patterns? If I give you a family of finite pattern, what do we want to do with it at the beginning? We really don't know what we want to do. So maybe you don't really know, but I think if I ask some children to do it, or I give them, for example, some jigsaw puzzle with an infinite number of an infinite number of pieces, but with a finite number of pieces up to isometry. Then I ask them, what do you want to do with them? I'm sure they will start to try to build bigger and bigger squares, even if they cannot think that maybe they will never answer the question whether I can go to the infinity. I think they will try at least some squares, some finite squares. And actually, if the subshift is empty, if I cannot tile with my jigsaw puzzle, the Z2, at some moment they will find a size n by n of squares that they cannot tile. This is a compactness argument. It's an if and only if. Okay? So it's like some kind of algorithm. I try to build all possible patterns of size n times n for every n. If I manage, I go to n plus 1. And if I don't manage, I answer no, your subshift is empty. But it's only a semi-algorithm because you may do this forever. So what can we do also? I'm rephrasing what I said. So the language of the subshift is co-computably enumerable. Co-computably enumerable means exactly this, that I have an algorithm which eventually says for each pattern when it's not in the language, but may not answer anything when it is in the language. So how can we deal with the other cases when to finally know at some point that my subshift is not empty? I can try to build bigger and bigger patterns such that the corresponding sides on the left and the right and the corresponding sides on the bottom and on the top can fold like if they were tiling a torus without involving in any forbidden patterns. So this is also something that I can try for every n, and I have another semi-algorithm which will tell me when I have a periodic tiling of Z2, a periodic configuration in my subshift, in the strong sense of periodicity where I have two periods. Okay? So does there exist an algorithm which tells me whether the subshift is empty? Yes, if I'm in a context where my system is always either either empty or contains a biperiodic configuration, which was the case in dimension 1 in SFT of dimension 1. Every non-empty subshift of dimension 1 of finite type contains a periodic configuration. So you could perform the two semi-algorithm in parallel. You ask half of the children to do the first one, half of the children to do the second one. Then you come back after maybe 2 hours. It depends on the size of the patterns, But you come back, if you don't give them any food until they will find at least one half of them will find, and they will tell the others, okay, you can stop, we have the answer. So this is an algorithm. The problem is, in two-dimensional SFT, you have this kind of things. You have a aperiodic subshift of finite type. So here I insist that this picture, maybe we don't see it very nice, but you have some kind of bigger and bigger squares appearing, which imposes the configuration not to have any period. But this is not very difficult to draw. What is difficult is that this is enforced by just by a finite number of forbidden patterns. In another way, there is a jigsaw puzzle such that the only possible ways to build an infinite tiling of the plane is aperiodic, and there is at least one way. And the first one was found by Berger in '64, and there were many others. So I kind of classified them in four big methods. Substitutions were the original way, and maybe can be seen as a dual of the most recent achievements, which is self-simulation, which can be seen as an active way of programming to enforce substitution. But the other two ways are quite different, actually. Encoding of
first row, is it for what dimension?
I'm talking about two-dimensional subshift of finite type. Z2. Okay. Z2. Everything is about Z2.
All this paper for Z2?
Yes. Yes. When I leave Z2, I will tell you, but it will be 5 minutes before the end. All of this is in Z2, and yes. Okay. Maybe just to. So nearly all of these constructions, which are not trivial, they give also a proof, indirectly, a proof that there is no algorithm to solve my emptiness problem. So if there were an algorithm, what was written just here is that if there is an algorithm, sorry, what is written here is that if there is no algorithm, then there are aperiodic subshifts of finite type. Because if there are no aperiodic subshifts of finite type, this more or less presents an algorithm. But it's not obvious at once that if there is an aperiodic subshift of finite type, there is no algorithm. There could be a completely different way. But actually, each of these methods, strangely enough, each of these methods rather directly also gives you result of undecidability, because very roughly you have some kind of hierarchy represented because your subshift of finite type must contain uniformly recurrent configuration, and you mark some hierarchy which will help you to embed computation everywhere in your subshift of finite type. The problem by just simulating a Turing machine like Wang did is that you may have a computation occurring in some parts of your subshift, but maybe also many periodic configurations, and this doesn't help you to prove undecidability of emptiness problem. But here we can define a subshift of finite type where every possible configuration embeds some kind of computation, in the sense that there are maybe you can see it as there are squares where you have little Turing machines that do non-trivial stuff.
Does it mean that each of these papers has a sort of not just one configuration but series of configuration, and then you're given a number of tiles and then you decide this question? Because
yes, yes. Basically, yes. There is each time there is one first result where they describe one subshift of finite type, and then there is a second result where they describe being given a Turing machine how to modify the subshift of finite type, which then depends on the Turing machine. Yes, except except this one, and that's why I added. But I mean, some years later, he did the second step, Jarkko Kari and Chulik. So we can say that two-dimensional subshifts of finite type are a computational model. So what can they compute? But let's have just a word about the main object that helped Berger and Robinson build the first aperiodic subshift. I think it's clear for everyone that this represents some kind of substitution. It's an object which is very natural already in one-dimensional symbolic dynamics. In one dimension, if you have a substitution, it means a map from A to the set of words over A, and you can naturally define a homomorphism of the free monoid, such that you apply successively the different letters. So in two dimensions, we just have to be careful. But if you have dimensions that go right, you can always put the squares correctly. For example, so if you define the map over the two letters which was above, I can define the map over a square, colored square, by the pile of squares which are the maps, which are the image of each of the first squares. And in this way, I can iterate, and I get bigger and bigger squares. And in the limit, I get by infinite configurations. There are several ways to formalize it, but one of the ways is to say that I take the bifinite colorings of Z2, which locally look like arbitrarily big iterated images of one of the letters. Okay? This is a notion of substitution, and there is a result which dates back from the 80s by Moses, which tells you that such a subshift defined by substitution is sophic. Recall that sophic means that it's a subshift of finite type to which I apply a projection of alphabet at each symbol, and this is very strong because in dimension 1, for example, sophic, recall that it's not much more complex than subshift of finite type. It's just regular languages. And basically, in dimension 1, I would say that maybe I can draw this picture. Sophic, you have sophic. So maybe inside sophic, you have SFT. But substitutive subshifts, like this, they are essentially disjoint. And you have some small intersection which corresponds to some finite case that are not interesting. But essentially, the people who study substitutive subshifts are not the same as the ones who study sophic subshift. It's completely different. But in dimension 2, what this theorem says is that this is the picture. Maybe I should still draw it a little smaller. Sophic, substitutive. And actually, many of them are SFT. Well, I don't know if it's clear. But this allows, by local rules, to encode many things, in particular to encode some kinds of hierarchy. And this is extensively used for all the following results, which talk about computation.
This particular example is sophic.
Yes. Yes. So I think.
I was looking in his article in Vesенny, yeah, and
yes.
This is this example.
Yes. It's okay. But okay, I think it's not so hard to see that it's not a subshift of finite type, but it's sophic, and sophic can be seen as also in another way as saying that I can decorate my letters. So that's why it's the contrary of projection of alphabet. I recall the alphabet from which I projected by decorating my letters, which help me define local constraints which force any configuration to have this kind of structure. And even better, if you have a sequence of substitution instead of if you instead of iterating the same substitution k times, you put a sequence of substitutions like this from a finite set of substitutions and following a given sequence of substitution, so it corresponds to saying that at each level I have the right to do something a bit different. And this is still Sophic, provided that the sequence is computable. It's very easy to, if it's not computable, then anything can occur, of course. But, okay, this is a result by Nathalie Aubrin and Mathieu Sablik. So, about our questions from the beginning, the natural dynamical questions, the entropy, I re-put the definition in terms of subshift. I take the number of possible patterns. I take the logarithm and I divide by n squared because we expect it to grow in exponential n to the square. I take the limit which exists. This can be proven. It's not so hard. It's not completely direct from the definition of entropy, but it can be proven to be a limit of a non-increasing computable sequence of rational numbers. That's how, I mean, if you think about it, that's how you would want to compute the entropy. But this doesn't mean that the limit is not necessarily computable, because a computable real number would mean that you have a sequence of rational which approach your real number, and you know the error. You know where you are, how far you are from the number you're going to. Here, you just know that you're going to this number, and you're going monotonously, but you don't know how fast you go to it. So there are uncomputable numbers here. And but still there are countably many, because you have one single program which outputs this sequence. And actually this constraint is an equivalence. Hochmann and Meyerowitz built SFTs for every such number, which is a limit of a non-increasing computable sequence of rationals. They built a subshift of finite type, which has exactly this entropy. About periods, there is a general theorem that's dated back from the 70s, Gurevich and Koryakov, that is more or less an application of the undecidability of emptiness problem up to some layer constructions, which says that it's undecidable whether there exists a periodic configuration in a given subshift of finite type. But even better, if you fix, I shouldn't say even better. Even better results are true, but I remove them from the slides not to make them too heavy. But another result, the set of periods, the set of numbers which occur as periods in a given subshift of finite type is in the class NP. So here we involve complexity theory. Just a remark, so these numbers have to be represented in unary, okay? If you represent numbers in unary, these numbers that occur as biperiod is in NP, and there is a result by Jandel and Vanier, which says that every set from NP, which is represented, which is included in the set of unary numbers, can occur as the set of periods of a given SFT. They can build an SFT exactly with this property. So again,
so it's an NP complete problem, basically.
Sorry?
It's an NP complete
yes.
problem.
This implies that it's an NP complete problem, but it's even a little better, because you can realize it's not up to a reduction, it's exactly every set can be realized as this. Yes. So again, the natural constraint that occur when you formalize your problem is actually the computational model that is S subshift of finite type is so powerful that you can reach this constraint and do whatever you want within this natural constraint. But here the constraint is from complexity theory, computational complexity theory. I didn't put a slide on transitivity because everything is quite easy when you assume this undesirability of emptiness problem. So I changed a little, I put something on uniform recurrence. And there is also such a result that the map, if you have a uniformly recurrent configuration, you can look at the recurrence function, which tells you the size of the window you have to look in to be sure to find something of a given size. And this map can be arbitrarily big, can be not bounded computably. Okay, for those who like groups, you can associate to subshift of finite type many kinds of group, the mapping class group, extended symmetry group. The automorphism group is maybe the most simple in some sense. The set of homomorphism that commute with the shift action. They can be seen exactly as reversible two-dimensional cellular automata. So, since they are reversible cellular automata, there is a natural, first it's countable, there is a natural set of generators, there is a natural enumeration of this group, and you can ask computability questions, like if I take a finitely generated subgroup of the automorphism group of a given subshift, what can I obtain? There were many, in the past few years, there were many results on what kind of groups can be achieved in these automorphism groups. So if you have a subshift of finite type which are very rich, like mixing and things like that, you can embed many things. But if you have a very low complexity, there are results that say that the group is not very big. But there are many open questions. One of the questions could be, what is the complexity of the word problem in such a finitely generated subgroup? And recently, with Emmanuel Jandel, Jarko Carrier, and Pascal Vanier, we proved that it can be as complex as any computably enumerable problem. So there is a reduction. Any computably enumerable problem, you can embed it somehow. So for those who are interested, it's a very strong reduction notion, which is stronger than any usual reduction in computability theory. So yes, but basically it means that naturally you can embed a computably enumerable problem in the word problem of such a subshift. In particular, it was a question asked by Mike Orman. There are such subshift of finite type which have an automorphism group in which some finitely generated subgroup have a non-computable word problem. Okay, this is, I will skip this. Okay, maybe another invariant. So if you have a two-dimensional configuration, you can always should be careful. Okay, yeah, okay. To any configuration, I can associate its central line, and if I take the set of central lines of configuration of a given subshift, I get a subshift of the dimension below, of a one-dimensional subshift. And if I take a subshift of finite type or a suffix subshift, I can take the set of central lines, I get a one-dimensional subshift, and actually it's always an effective subshift. What does it mean? It means that I can enumerate a set of forbidden patterns which define this subshift. There is an algorithm, a semi-algorithm, which produces defining family of forbidden patterns. So F may be infinite. We are very far from the subshift of finite type case. The one-dimensional trace may be very far from a subshift of finite type. But still, there are countably many of them. And it has been proven by all of these people that actually every effective subshift can be obtained this way. So this is a very, very strong result. I don't know if you really realize. If you tell me, if you describe, basically if you describe to me a set of bi-infinite configurations, one-dimensional configurations, you describe them by, without talking about Turing machines, but by simple mathematical statements, then most probably your set will be an effective subshift. And then I'm telling you, we can build some kind of jigsaw puzzle such that the only way, you take all the possible ways to fill Z2 with this jigsaw puzzle, and there is an alphabet projection such that when you take the lines, you take exactly the set that you wanted to realize. In particular, it allows to recover some old results. So here I'm talking about Kolmogorov complexity for those who know. If you take the Kolmogorov complexity of a pattern, it means the size of the smallest program that describes a pattern. So it's quite obvious. The definition is obvious for a one-dimensional pattern, but it's not very difficult to also build programs that draw some finite matrices. And in a subshift of finite type, and even in suffix subshift, well, you can see that the complexity cannot be in n squared. It has to be at most n. And n is the size. So possibly, if you take any pattern, it could be in n squared, the number of bits that you have to draw to define this pattern. But the maximal complexity, which is allowed by this, can be reached. So this result means that you can build a jigsaw puzzle such that all possible tilings of Z2, whenever you take any square anywhere in this, there is no simple description of it. In particular, there is no square with only zeros, for example, for n big enough.
Maybe I don't understand. If we just take like a periodic coloring with if you take just periodic coloring with period 1, like or containing consistent like of vertical lines, for example, and then
so there exists a subshift of finite type which has this property. In particular, this subshift of finite type will be aperiodic. It will be a very complex subshift of finite type.
Subshift with what property?
There is a subshift of finite type such that for every configuration in this subshift and every pattern that you take in this subshift, it will be very hard to describe. So in particular, there will be no periodic configuration.
No, so it's like you said, it's the size of the window is n squared, yeah? It's
yes.
n1. And the complexity is n, yeah?
Yes.
So what the example I'm talking about is like you take just all the following subshift of finite type there. You say that the color of a cell and a cell below it would be the same. So it's just so obviously complexity will be bounded by n, but also there are configurations with complexity exactly n.
But here it's a subshift of finite type.
Yes, and it is of finite type, of course, because it's a local constraint. I just say that.
No, but here, okay. But here it's for every configuration. In your subshift, you will have you just take the subshift of finite type. Yes,
yeah, for every.
every configuration is very complex. In your configuration, you will have many periodic ones and simple ones. Okay. Maybe I will skip this. So another invariant is which is quite linked to the traces also is the expansive directions. Expansive directions means that if a subshift has an expansive direction like this, it means that there is a stripe with this direction, and whatever colors I put in this stripe, there is at most one way to recover a valid tiling of Z2. It's a very strong, it's a very strong property. And the set of expansive directions is open because of some kind of compactness. There is some kind of cellular automaton, in some sense, which is you need to do some kind of grouping of the colors, and you need to turn your head depending on the direction. But there is some kind of local rule which tells you how to go in the two directions. So it's open, and it's even effectively open, which means that you can really program to find an open set of directions which is expansive. And actually, this was a question asked by Mike Boyle. We can prove that every effectively open set of directions can be realized as a set of expansive directions of one given SFT. And there is also another informal statement which says that everything I said so far, even when I restrict and I say that nearly all directions except one are expansive, then every computation result I said so far is still true, which means that when you restrict, when you constrain a lot your subshift of finite type so that you can see this constraint more or less as something to say, something that is in between dimension 1 and dimension 2, because we saw that in dimension 1, subshift of finite type were rather simple. In dimension 2, they are very, very powerful computationally. And if we constrain and we say that it's dimension 2, but there is a dimension 1 which is in bijection, and then everything is still very complex, except one thing: the characterization of entropy. This implies entropy 0. But if you change and you look at directional entropy, which is another way to count the patterns, then you still have the same characterization as before. By the way, if you know about group automata, this property about expansiveness can also be seen, has a lot of links with automata groups. Automata groups. Because you can always, so if you see an automata, maybe I don't do the definition now for people who don't know, but very quickly for the others, an automata group is something that acts on infinite sequences, depending on a finite, because let me write a binary word here. And if I have a state of an automaton, an automaton is something that, given a state and a letter, gives me a new letter and a new state. And if I continue like this, there is always a way to extend. And there is a one-to-one correspondence between, if you now shift to see this as bi-infinite, which is nearly the same as mono-infinite, there is a one-to-one correspondence between the orbits, between the sequence in an orbit of an automata group and, let's say it this way. There is a one-to-one correspondence between automata groups and subshift of finite type with up to conjugacy and with very strong expansive properties. And in particular, reversibility, bireversibility, and things like that can be expressed in terms of the set of directions of expansiveness of the subshift of finite type. In some sense, this has been used, maybe not exactly with this vocabulary, to prove by Pierre Gélibert to prove some undecidability results on automata groups. Yes, so well, okay, that's so. Since we saw that in two-dimensional subshift of finite type, we are maximally powerful and tremendously more than in one dimension. As I said, you can try to constrain to understand where the border lies. So this can be done in terms of expansive directions, which more or less corresponds to deterministic directions. There was also a topic about computing with errors. So you require your subshift of finite type also to be able to do some computation even when there are some noise. You can require minimality, and this has been done recently by Bruno Durand and Andrei Romachenko. So this is about minimizing the set of tiles. Okay. You can ask about what differs between the different methods that I presented about the proofs of aperiodicity. And you can also ask in general about groups, what happens if it's not Z or Z2. And if I put colors, for example, in such a Kelly graph, so I have a natural way of defining subshift of finite type in a Kelly graph or in a group with finite number of patterns that are forbidden. So same questions as before. What can I decide among the natural questions? So here, for the free group, actually everything will be as decidable as Z because, so there are several ways of seeing the reason, but essentially there is a tree automata theory that works quite well. And another way of seeing this is that you cannot embed computation because there are too little communication between the different parts of the graph. But at least what we already know is that every group which embeds Z2 has a strong computational power. By strong computational power, if you don't like my vague sentences, maybe you can just ask, is the emptiness problem decidable? For the emptiness problem of SFT defined on a given group, is it decidable? And it's decidable for every free group. It's decidable for every virtually free group because finite index subgroups don't change a lot. And actually the conjecture is more or less that's all. Some hints to support this conjecture is that non-virtually free group, they all embed some grids, but in a graph theoretical sense, which is very non-uniform. So the non-virtually free group, their Kelly graph has an infinite tree width, and thus they have minor, in the graph theoretical sense, which are grids, arbitrarily big grids. So you want to do some computation inside, but it's hard because this minor is usually very non-uniform. You cannot encode it with local constraints. But still, what is known is that on non-virtually free groups, there are some logical statements which are undecidable, which are written only in monadic second-order logic, which is just quantifying. You use the neighboring relation, for example, and you quantify on the elements on the group and on some subsets of the group. Here, for example, the emptiness problem can be expressed in this logic because the colors of the alphabet that are used can be seen as can represent subsets of the group. You have finitely many of them, and you can express a statement like this. So there is a non-decidable statement for every non-virtually free group, but we don't know if this statement, the SFT emptiness, is undecidable. Yes. So to conclude, maybe what you can just remember is that one-dimensional SFT, I'm talking a bit like a computer scientist. One-dimensional SFT is a dynamically inspired model which is as powerful as finite automata. Two-dimensional SFT is a dynamically inspired model of computation which is equivalent to Turing machines. In some sense it's equivalent, but intrinsically it's very interesting because it can represent some kind of parallel model of computation much more than Turing machines. Yes, I can point that the fourth point here, what does it mean? Many results that I stated, for example, the one on traces, which was saying that when you reduce one dimension, you can go from finite type to effective. So it means finite number of constraints. I reduce the dimension, I'll do a projection of alphabet, and I obtain a subshift which is any subshift with a computably enumerable family of forbidden patterns. This can be seen as an analog of Higman's theorem on countable groups. And this analog has been formalized in a paper by Emmanuel Jandel because they are both subcases of what is called closure space. So actually, subshift can be seen as a parallel as groups, and subshift of finite type is subshift is the same as finitely generated groups. Subshift of finite type is the same as finitely presented groups, and effective subshift is the same as effectively presented group. So this paper is quite interesting, even if the results are not so new, because it's really a parallel between two theories that existed, but it gives generalization of them. Among the open problems, so we've seen that the suffix subshift can be very, very complex, but still there are some combinatorial constraints. We saw, for example, the Kolmogorov complexity, which cannot be completely maximal. So it would be interesting to understand a little better what are the suffix subshift. What makes, for example, if you are given an effective subshift, of course, if you are given a subshift which is not effective, there are some uncomputability which is too strong, it cannot be sophic. But if you're given an effective subshift, it's not clear when it will be sophic or not. When I can find this set of pieces of jigsaw puzzle together with an alphabet projection which realizes exactly this set. This I already told. Yes, and yes, I already spoke of this. Complexity theory is okay. Is a natural question when you're talking about a model of computation. So maybe for computer scientists, the complexity theory, we saw one case where it was nicely adapted from the classical complexity theory. But is there an intrinsic complexity theory that would use really the power of subshift of finite type as a different computational model? Thank you very much.
If there are any questions, you can ask.
I want to add to your very big list of papers our old paper 92 with Alexander Lifshitz. It was one of the first papers for two-dimensional substitutions, and special example of what is also a subshift of finite type. It was, I think, it's very interesting example which unfortunately never continued, and I recommend you to look at this. Is a so-called cross. There is some map from Z2 to Z2 expanding, and you obtain some kind of growth of the configuration, and several problems was put, but mainly it's still open. It's very interesting. And I want to say that also there is a paper by an American mathematician, I forget his name, from Berkeley, who consider subshift of finite for Z2, subshift on finite type with some unexpected property of entropy. I forget his name.
Tom Meyerowicz? No.
Huh?
Tom Meyerowicz? No, it's not Tom Meyerowicz. He was
no.
Because there is a character.
He came from ergodic theories.
Oh yes, that's the case. Okay.
And reference I can give you.
Ah yes, thank you very much. Yes.
Any more questions?
I have a question. Maybe we discussed it some time ago, and maybe I have forgotten. But the question you mentioned about the different groups. So, what about the surface groups, and what about the hyperbolic groups? Whether the answers are known about the emptiness problem. Yeah.
Yes, good question. So, yes, I didn't have time to mention everything which is known. I think everything which is known is that for virtually free group, okay, this is okay. So, on the other direction, every group which embeds Z2 has an undecidable emptiness problem. Surface group also, and it's a recent work by Nathalie Aubrin, Sébastien Barbieri, and Étienne Moutot, and one of them strongly, even nearly claimed that it could be extended to all hyperbolic groups, but I think so. In these groups, the being given a subshift of finite type, it's undecidable whether it's empty. Being given a finite number of constraints, it's undecidable whether it's empty. We're expecting this to be true for all non-virtually free group, even though it's still far. Also, there is a work by Alexis Ballier and Maya Stein which proves this for all polynomial growth groups. Polynomial group, non-virtually free.
Markets improved the undecidability of tiling problem for surface groups.
Okay, and does it intersect the? I remember there was something on this, but I think Etienne told me about this, and he knew about it. So you know that if it intersects the work by Nathalie Aubrin, Sébastien Barbieri, and Etienne Moutot?
That is previous.
Okay, and he also proved, of course, translation of subshift of finite type, not over groups, but in a hyperbolic plane. And he worked a lot on this. Yeah. And yes, Morgenstern. And there are also works where to build. There is also the question of aperiodic subshift of finite type, which is quite active, and also Chaim Goodman-Strauss had results on all hyperbolic groups, I think. But here he doesn't have the embedding of the computation, which gives the undecidability. Let's still early.
Yeah, I think we can have one.
You mentioned automata groups and showed how automata acts on infinite strings. So can you give an example of interesting example of automata group?
Yes, depends how long. So
yes. One minute. Okay.
So what I claimed is so I'm sorry, I said it very briefly and maybe a bit vaguely. What I just said is that from any automata group, I can build an SFT, and the properties like bireversible, reversible, injectivity, and all of this can be directly translated in the set of expansive directions. And for example, for example, the Bernstein problem in a class of automata groups can be nearly directly translated into the question whether there exists a subshift of finite type which is not uniformly periodic, but every configuration with a periodic column is periodic. So this kind of translation. I didn't claim any deep result. I'm just claiming, and even this correspondence is not only my remark. It is present in work by Gilbert and also in the PhD thesis of Thibaut Godin and things like that. But it's just a correspondence. So it's interesting to see links between in particular, undecidability questions in the two sides, in symbolic dynamics and in automata groups.
We can continue. Let's thank the speaker again, and we can continue with the line.
Thank you.